In this video, I'm going to talk about units in radio astronomy. Suppose we have a source in the sky. Radio astronomers usually talk about a source in terms of a brightness temperature. This brightness temperature is related to the specific intensity, I nu. In the Rayleigh-Jeans approximation to a blackbody, the specific intensity is given by 2 times the Boltzmann constant times temperature over the wavelength squared. When astronomers talk about the brightness temperature, this is the temperature that they're referring to. The units of specific intensity are power per area per hertz per steradian. Now suppose we have our source in the sky, but we also have a telescope that we make an observation with. In effect, what we're doing is we are integrating over the angular size of the source. This turns the specific intensity into a power per area per hertz. In other words, this is a flux per hertz. This is usually denoted as a flux density. We usually measure a flux density in terms of a Jansky. A Jansky is equal to 10 to the minus 26 watts per meter square per hertz. One important thing about the flux density is that as long as a source is unresolved to a telescope, and all telescopes can agree on the flux density. That is, if the source is unresolved, meaning that the antenna beam is bigger than the angular size of the source on the sky, then all antennas with this property can agree on the flux density. However, if the source is resolved, meaning that the beam is actually smaller than the source, than the angular size of the source on the sky, then we usually talk about the flux per beam. And this, in effect, is the same thing as the specific intensity, and all antennas will agree on this flux per beam. This leads us to the conclusion that the specific intensity is an intrinsic property of the source. Now let's talk about actually receiving the signal from the source in our telescope. In this case, we only receive what our antenna can catch. That is, we integrate the signal over the aperture of the telescope. And this gives us, from the flux density, gives us a power per hertz. This is sometimes called power spectral density. In fact, this is what a spectrum analyzer reports, although they often forget to report the hertz part of the power per hertz. Now, once our antenna has the signal, we feed it down through some type of filter. When we feed it through the filter, we are integrating over the bandwidth. Hence, we are left with power. Power is usually measured in volts squared per resistance, which is usually taken to be 50 ohms or 75 ohms, depending on what kind of system you have, but it can be anything. Watts, or dBm, which is a decibel. Note that volts squared over R is the same thing as watts. The formula for converting between watts and dBm is as follows. If you measure a power in watts P, then in dBm this will be equal to 10 times the log of the power in watts to a milliwatt. After we integrate over bandwidth, we integrate over time. And this gives us energy.